Welcome to part 2 of the this mini series on observability. In this lecture, we're going to go over nonlinear observability. If you haven't watched the one on linear observability, I recommend you do that first, just so we're on the same page in terms of notation and the overall narrative of the presentation. So for a nonlinear system, we could write out a generic form as x dot equals some nonlinear function f of the state x and some control inputs u. Now here we're going to focus on a specific class of nonlinear systems that we can put in control affine form. So for these systems, we could write this out in a little bit more of an organized fashion, given the drift dynamics, f0, which are only going to be a function of the state. So that would be what happens if you turn off all of the controls and you just let the dynamics evolve naturally. Then we may also have some dynamics that are due to the control inputs. So we might have some control input U1 that would lead to dynamics that are described by F1 of X. And we could have as many control inputs as you could envision, all the way out to UN, and I'm going to abbreviate this to just FN. So in addition to the nonlinearities in the state dynamics, there may also be nonlinearities in the measurements. So we'll call those measurements y, and those will be given by some nonlinear function h that is a function of both the state and the control inputs u. Now, just like in the linear case, we may get lucky, and maybe it's possible to, in principle, estimate the state given the measurements that are given right now at one point in time. In order for that to be the case, there need to be as many unique equations given by the function h as there are states. So if there's n states, then you need to have n unique equations in h. Now, one quick note on what it means to be unique in this case. If one of those equations is x, then x squared does not count as a unique equation, because if you know x squared. There's no new information given in there. So this makes it a little bit more difficult to evaluate, but we will talk about some convenient ways to do that later in the lecture. Now, of course, in many cases, you may not have enough information at one moment in time to estimate the state x. But again, just like in the linear case, if you have a whole sequence of measurements, you could take the derivative of those measurements and gain some new insight from that. And for nonlinear systems, it turns out you could get a lot more information from that, depending on what is happening with the control inputs. So for the nonlinear system, for our derivative, we will have y dot is going to be equal to the time derivative of our measurements, h. Now, using the chain rule, we can split that up, and we can get the derivative of h with respect to the state, multiplied by the derivative of the state with respect to time. That is, of course, assuming that the measurement description, the equation h, of course, does not change with time. If that did, then there'd be all sorts of other problems. So just like in the linear case where we replaced our x dot with ax plus bu, here we can replace that x dot with this equation up here. So we can get that our y dot is going to be equal to the derivative of h with respect to our state x times, and I'm going to shorten things here just for simplicity, we have our f0 plus u1 f1 plus all the way out to un fn. So now we can see what happens if we choose different values of controls u. So we're going to move on to a new page here. But if we chose all of our controls to be 0, so if u1 through n were all equal to 0, then we would have y dot is going to be the derivative of h with respect to our state times f0. And we can ignore all the other f1 through n because those control inputs are turned off. Now we're going to write out a lot of derivatives like this, so it's convenient to write this out with a more compact notation. Also note what this means. What this equation here, what this means is we're taking the derivative of h along that the vector field of f. And this is known as the Lie derivative. And so we can write this out a little bit more compactly as the Lie derivative of h along vector field f0. We can take this Lie derivative along all sorts of different vector fields, as we'll see later. But first, let's get a little bit of intuition comparing this nonlinear case to the linear case. So if we were to linearize our nonlinear system around some nominal state and control, then we could write out our measurements and the derivative of those measurements as the Jacobian of h evaluated at that nominal state and control, and the Jacobian of the Lie derivative of h along f0, also evaluated at x0, u0. And all of that is going to be multiplied by x. So now hopefully you can see the parallel between that and the linear case where we had c and ca multiplied by x. So if we evaluated the rank of this equation here consisting of the Jacobian of those measurements and the Lie derivatives, and if that was full rank, then that would mean that at least at that particular operating point, the system is observable. Now it could be that if you move to a different operating point, that like a different value of x0, that then your system is unobservable, and that's simply a fact of nonlinear systems. So really you would have to check this at all the operating points that you really care about. Alternatively, you could try to find the degenerate cases where the system becomes unobservable for specific values of x0. Now let's think about what happens if one of the controls is not 0, but all the other ones are. So if u1 is not 0 and all other controls are, then when we look at the derivative of our measurements, y dot, we will have the derivative of h with respect to our state. We still have those drift dynamics, those don't go away. But now we'll also have the derivative of our measurements with respect to the state times f1 of x times u1. So again, we're going to simplify things with our notation. Here's where you can see that becomes a little more convenient. I'm also going to drop the little arrows above all of the vectors just to save some space and time in notation. Now, if all we're doing is trying to understand the binary yes or no observability, we can replace that u1 with the value 1 without any loss of generality. So that will kind of simplify things. So we'll replace that with 1 there. Now you could imagine doing this for every single control input that you have. And in the future, we'll talk about all the different kinds of combinations. So if you were to do this, we're going to call that collection of things that you would get G, and I'm going to put a little 1 up here to note that this is only considering the first derivatives. So this is called the observability Lie algebra, and we'll have H. We have our first one that we talked about, just the drift dynamics, so all the controls are off. Then we have this one that we just went over here, LF0H plus LF1H. And then you'd have this for all of the control inputs that are available. So we would have LF0H plus LFNH and so on, or yeah, up to that, right? Now, to evaluate what's going on, we can simplify things a little bit. Because LF0H is in that list, we can actually, for the purposes of analyzing the observability, we can get rid of these terms here just to simplify things a little bit. So we'll have G is going to be H, LF0H, all the way out to however many controls we have. Okay, so now we can again count all of the terms that appear in that observability Lie algebra. And if we had n states and there are n unique terms in that collection, then we know that our system is, in principle, observable. Again, as we discussed, that's a little bit difficult to determine sometimes. So a convenient way to do that is to calculate the Jacobian of G, and we'll call that O, just like we had an observability matrix for the linear case. This is going to be our observability matrix for the nonlinear case evaluated at some specific operating point. So O here is going to be the Jacobian of that G evaluated at some operating point, x0, u0. So that's going to be some matrix, just to give you a little bit of intuition. The columns here are going to correspond to the states, just like in the linear case. And the rows here are going to correspond to all of the equations or expressions that you found in G. So these are going to be your terms from G. So far we've just discussed what happens if you take that first derivative. Of course, interesting things can happen if you take second derivatives. So there are a variety of second derivatives that you could take. We'll just go over a couple of those here. So you could have the second derivative of just the drift dynamics. So that would be LF0, LF0H, and we can abbreviate that to be L squared F0 of H. So that would be just like in the linear case, if you just let your drift dynamics drift with no controls and you calculated the second derivative, that's what that term is telling you. You could also see what happens if you turn on your controls and then turn them off and let the system drift and determine the second derivative that way. So that would be, say, LF0, LF1H. That one we can't really abbreviate anyway. We could also alternate controls, so we could have LF2 and then LF1, or the other way around. And that way you can start to see that you can accumulate a lot of terms very quickly. And for that reason, it is convenient if you can try and implement this using symbolic algebra. And we will have a little lecture about doing that later on in this series. But for that, that's all we have for this lecture.